Okay, so we start from where we ended last time. We derived this adaptive filter, not derived, I presented this famous adaptive filter algorithm called LMS, least mean square. Based adaptive filter. Okay, the equation was like this. At any nth stage, you do three operations. At any nth clock, that is nth stage of iteration, that is clock, nth clock, because one iteration per clock, you are doing three operations. One is filtering, that is filter output is yn is equal to Wn transpose xn vector. Okay, which is nothing but you can write W0, have to put an n because even if it is a 0th coefficient, it changes from n to n. Xn plus next coefficient W1 in dot 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 dot, this is the filter output, which is nothing but W transpose n xn. Let me remove this last coefficient is this, all are function of n because they are adaptive, they are changing from clock to clock, and the data sample here is, this is the meaning of this filter output W transpose xn. So, that is first what we do, we are assuming Wn is already available, that is the filter coefficients, all these coefficients to be used at the nth clock are already computed or evaluated from the previous clock. So, we just simply filter the input like a FIR filter and calculate the output yn, that is number 1. Then error computation. You calculate error En as given desired response Dn minus Yn, this Yn is filter output. Then you update the weight vector Wn to a new value Wn plus 1 by the LMS formula, and the Wn plus 1 you hold till the next cycle comes, then you give it to the filter, then Wn plus 1 vector will be used as the new filter at n plus 1th clock. So, weight, you can say weight adaptation, adjustment, update, I prefer the word weight updating. You can also say weight adaptation or adjustment. So, you generate new weight vector from previous weight vector and mu times xn vector En. Remember, xn is a vector, but En is a scalar. So, En multiplies all the elements of xn. Typically, it is a vector. Typically, it means if you take the 0th coefficient, W 0 n plus 1 will be W 0 n, or maybe I just you can write, if I want to write in a vector form, it is like this: W 0 n plus 1, W 1 n plus 1 dot 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 this is vector, this is nothing but W 0 n plus mu x n vector into scalar E n. That is, if I write it in expanded form, it is like this. Okay. Now, I have to develop an architecture, a circuit which will do all these calculations. There is filter output calculation, calculation of this and calculation of this at every nth cycle. Okay. Therefore, for that, first start with input x n. You have to do it like an FIR filter x n into W 0. It is a function of n, but suppose W 0, x n minus 1 into W 1 dot 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 x n minus capital N plus 1 into this W capital N minus 1, and they are summed. It is like a convolution sum, typical FIR filter. For this, you have to proceed like FIR filter. You have to assume that these coefficients W 0 n, W 1 n, all these are known, they are available. Next step will be subtract this output y n from d n. Then is the most important step, from using E n and the given x n vector. Okay. Calculate new weights, each coefficient. See, all the coefficients are used here, W 0 n used here, W 1 n used here, all these are. So, now they have to be updated by adding an extra term. There will be the new values for n plus 1th clock. So, I will be holding them in the n plus 1th clock, I will be using them for filtering to generate y n plus 1, and it will go on like that. Okay, this is the meaning of this. Okay. So, therefore, I go to the circuit directly, I will come back to this page again if required, take the input, x n. X n will be multiplied by like an FIR filter W 0, but here W 0 is a function of n, it changes from clock to clock. Then there is a delay, then it is multiplied by W 1 n, again a delay, multiplied by W 2 n dot 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 dot, last one more delay, and multiplied by last coefficient, it is a function of n, and then you have to add them. You can put a plus and 0. So, basically whatever you have, that only comes, then this gets added with this. We have already done this kind of things while doing signal flow graph for FIR filter. You just have to refer that. Only coefficients are here, function of n, multipliers. Then again this addition, multiplier, this addition, it will get added like this, dot 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 dot, yn will come up. This have to be subtracted from dn. This is your en. You multiply by mu. So, mu into en comes. Okay. Now, I have to generate W0 n plus 1, W1 n plus 1, W2 n plus 1 and hold them in flip flop and they are released in the next cycle, right. How to generate W0 n plus 1? So, we come back to the previous equation, previous page. W0 n plus mu en into xn. W1 n plus 1 is W1 n plus again mu en into xn minus 1, so on and so forth. So, just that mu en is already available, okay. That into xn, mu en into xn plus W0 n. So, if it is W0 n W0 n plus mu en into xn, they are added. This output is your W0 this is W0 n plus 1. W0 n plus 1 by the formula. What is W0 n plus 1? W0 n plus mu en times x of n, mu en times multiplication x of n drawn from here, that and W0 n assuming it to be available is given here. So, W0 n plus 1 come. This I will be holding in flip flop in delay and release in the next cycle. So, next cycle this will come here. It will generate new W0, W0 n plus 1 and loop will continue. This is the weight update loop for W0 n coefficient. Then W1 n, again you see how to generate W1 n plus 1, mu e, I mean to W1 n you add mu en times x n minus 1, W1 n plus mu en times x n minus 1. So, what you do is mu en is already taken, x n minus 1, so x n here, x n minus 1 here. So, from here now you tap the same line. Okay. Sorry, there will be multiplier. This multiplier. So, mu en times x n minus 1, that has to be added with the W1 n. So, they get added and the output I hold in a flip flop, hold in register delay. This is your W1 n plus 1. In the next cycle it moves here. You can do a few more also. If we had W2 n plus 1, it is W2 n plus mu is n minus 2. Okay. So, W2 n and mu en times x n minus 2. X n minus 2 is here, x n minus 1, x n minus 2. So, from here you take a tap. same guy here, it gets added with so this will be your W2 and again this will be put in delay like that. And lastly, you can verify or you can even check now. Last coefficient, so this much of x n minus capital N plus 1, that is to be multiplied by mu n added with this coefficient. Okay. So, you can take again another tab from here. In this again you can have multipliers. Same structure. So, this will be your W. Okay. So, this is the basic structure of an LMS based adaptive filter. What is the critical path? Critical path will be, you see, you start from here, this multiplier, this multiplier, the multipliers are in parallel. So, take one like FIR filter, multiplier is parallel. So, take one of them and go on following the adder line. So, one multiplier and so many adders, then again this is also an adder subtractor, but this subtraction and addition they are equivalent. So, this is the line, one multiplier, so many adders, then again a multiplier, then these are parallel structures. So, you can go up to either this and then up to this, that is all. Okay. And then there is a delay, or you can try here, they are parallel. So, this is a critical path. I want to bring down the critical path. I want to, like an FIR filter retiming, here also in the adder chain, all the additions they are coming one after another in the same cycle. So, I want to insert delay here. If you want to insert delay here, I will try to do cut set retiming. So, what I will do, here I want a delay. So, suppose I cut like this. So, this is one direction edge, this is one direction and this is reverse direction. I want to have a delay here. So, if I want to have a delay here, this will become D, this will become 2D because they are in the same direction, and from the opposite direction I should take out one delay. But is there any delay in this edge? No. So, it will become negative. So, I cannot do retiming. Similarly, if you want to do here, if you want to insert a delay here, you have a cut set. Hold on. I want to have a delay here between these two adders. So, I will be cutting like this. So, I want to have a delay here, this is one direction, same direction on this side. So, if you want to add a delay here, it will become D, it will become 2D. From the reverse direction, I have to take out delay. Now, reverse direction there is one edge, another edge, but none of them has delays. So, I cannot take out any delay, so on and so forth. So, this structure is good, but you cannot do any retiming on it, okay, because there is a loop, feedback loop, and the feedback direction there is no delay in the edges. There is a reason I cannot take out delay from that direction and insert them in the forward direction to bring down the critical path. That is, I want delays to be between every two adders here, like I did in the case of FIR filters earlier. Okay. to bring down the critical path, but the moment I try to put a delay in this direction, and therefore, I have to have another delay in this edges, they are in the same direction. I have to take out delay from the opposite directions from these edges where it is cutting, but there is no delay in this direction. Okay. That is the reason we cannot do. So, as such LMS algorithm is good, but when it comes to retiming and all that to bring down critical path, this algorithm is no good. You cannot retime the architecture to speed up, that is to pipeline it. For that, LMS algorithm is to be changed to another version called delayed LMS. Okay, another version called delayed LMS. I'll go to that delayed LMS. But before that, something more we have to see. I come back to that retiming theorem part. Consider a special case. I said that if I divide the given DFG into two parts, at that time I took one source, signal source, and I put it happily on this side. Now, I will have two sources, one on this side, one on this side. Okay. And suppose I have got some nodes, they are all internally connected as before. And there are one set of edges in this direction, they are not changing, and another set of edges in this direction, some delay L1D, L2D, LRD, I do not know what notation I use that time, this could be small m1D, small m2D, dot 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 small m, maybe p d. Okay. So, from one direction you have to, in one direction you have to add constant number of delay, and from the opposite direction take out the same amount of delay from all the edges, making sure that none of them turns out to be negative. That much we said. We that time considered only one source. Now, I am considering two sources. Now, suppose it is coming to this node and this is coming to this node. Okay. If I choose n here and the retiming value m here, and suppose m is greater than n. So, as I know, if I follow the retiming theorem, if this has original delay, whatever be the delay, that plus n will come, that many delay, and here plus m, whatever be the delay in this edge, plus m will come. If m is larger than n, what you can do? You can absorb this n delay in this, again here also n delay. That is, if there are two sources, okay, if you want to take, absorb the constant number of delay, then same must be true for all the sources. You cannot give a delayed signal here and non-delayed signal here. That is, if there are two signals, say maybe x1n, here you are getting suppose x1n. Here I am explaining this, here you are getting x2n. So, x1n, so there is a system where, just a minute, we have got a system that is taking two signals. It is generating various outputs. Every node output is an output, right. Now, if you want to delay one input, you have to delay the same. That is, if both the inputs are delayed by the same amount from your, that is, both the inputs arrive after the same amount of time together, your system outputs will not change, every output will be delayed by the same amount. It is just delaying the entire thing. But you cannot give one delay here, another delay are different, then it will be completely different. That is, instead of giving x1n coming down or x2n coming down, if they come after 2 cycles here, after 2 cycles here, entire operation of the circuit also will be delayed by the same 2 cycles, provided both are delayed by the same amount. But if you want to give delay x1n by say 2 cycles and x2n by 3 cycles, then there will be problem. Then the outputs will no longer be same as previous one with some constant delay. It is not. So, as long as both the inputs are delayed by the same amount, entire thing of the circuit also gets delayed by the same amount, just delaying the entire operation. So, suppose m is greater than n. So, I delay in this input here by n, here also I delay by n, which means here I will absorb the delay. So, my input will be x1 n minus n. Here again capital N, same delay has to be given. So, net delay that will be left with is m minus n, n will go inside and the input here will be x2, this is also delayed by the same amount. So, both the inputs to the entire system delayed by same amount capital N, and therefore, all node outputs also will be delayed by the same amount capital N, but I am left with what in this side, I mean whatever be the delay I had here, that remains as it is, nothing gets added. Here whatever was to be added plus m, that gets reduced by a factor n. As a special case, suppose n is 0, as a special case and m is 1. So, before retiming I had whatever delay, this is 0 here, okay. I mean whatever delay I had and whatever delay I had, this will remain unchanged as before and this will get reduced by m1 n0. So, 1, I mean it will be just added by 1, okay, it will be added by 1. That means, this edge will have no addition of delay, this edge will have an addition of 1 delay, because n is 0, m is 1 as a special case. So, whatever delay I had here, that plus 1 minus 0, that means 1. So, whatever delay I had in this edge, that will get added by 1 delay here, here nothing. Okay. This you remember, this I will be using while retiming the delayed LMS algorithm, which we will discuss first. Thank you very much.